These may be among the most colossal explosions of radio energy in the universe, releasing energy equivalent to 1 billion suns. The sheer power and radio frequencies generated by these blasts are so extreme that they have finally caught the universe's attention. The James Webb Space Telescope, JWST, known for providing profound insights into the universe's deepest secrets, has uncovered something alarming. Betelgeuse, a star famous for its brilliant presence in our night sky, has shown signs of a potential cosmic explosion event in 2023. As we contemplate the implications of such a divine event, an intriguing revelation from the past comes to light. The enigmatic supernova SN 1987A could hold significant clues about Betelgeuse's future. What could this mean for our own planet? Join us as we delve into this cosmic mystery. Since its launch, the JWST has been at the forefront of astronomical discovery. Its advanced instruments and unmatched infrared capabilities have allowed us to explore the most distant regions of the universe, revealing long-hidden mysteries. One of its recent and unsettling discoveries pertains to Betelgeuse and its possible cosmic explosion event in 2023. Before we dive into the mysteries surrounding Betelgeuse, it's essential to understand another significant cosmic event: the explosion of SN 1987A. This supernova serves as a crucial benchmark, offering valuable insights into the life cycles of massive stars and their dramatic endings. It helps us appreciate the behavior of stars like Betelgeuse. Recently, the JWST's near-infrared camera captured detailed images of SN 1987A, revealing its complex structure. This supernova was first observed in 1987 when astronomers detected one of the brightest celestial explosions in the night sky. It emitted an enormous amount of energy, creating a brilliant flash of light visible from Earth. SN 1987A remains one of the closest supernovae observed in centuries, and since its discovery, astronomers have closely studied its expanding debris to better understand stellar evolution. SN 1987A, resulting from the explosive death of a massive star, is located 168,000 light-years away in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. This supernova radiates across the entire electromagnetic spectrum, from radio waves to gamma rays, and has been studied using prominent observatories such as NASA's Hubble and Spitzer space telescopes and the Chandra X-ray Observatory. However, the JWST has provided a unique perspective on this famous supernova. Its near-infrared observations have captured the most detailed images of SN 1987A, showcasing its complex and external rings, bow-shaped internal ejecta, and distinctive keyhole structure. The center of the JWST's image reveals dense clumps of gas and dust expelled by the supernova. This dust is so thick that even the JWST's near-infrared light cannot penetrate it, resulting in a dark region in the keyhole. Surrounding the internal keyhole is a bright central ring formed by debris ejected thousands of years before the explosion. This ring also contains glowing hotspots created when the supernova's shockwave interacted with the ring structure. The JWST's sensitivity has also uncovered new crescent-shaped structures believed to be part of the supernova's outer gas layers. While neutron stars typically form after supernova, the one in SN 1987A remains elusive due to its dense core. This explosion likely marks the death of a blue supergiant star, one of the largest and brightest stars in the universe. As we've seen with SN 1987A, the universe is full of strange phenomena. Now, Betelgeuse may be the next cosmic enigma to intrigue us. Are we on the verge of witnessing another celestial event that could rival or even surpass the awe of SN 1987A? NASA astronomers are eagerly awaiting developments, having made a discovery that has stirred the scientific community. Betelgeuse, known for its steady brightness, has started to dim, not gradually, but abruptly and noticeably. Observations from the JWST indicate that the star's brightness has significantly decreased over a short period. What could cause such a rapid dimming? Betelgeuse is no ordinary star. It is a red supergiant with a diameter over 1,000 times that of our Sun. If positioned at the center of our solar system, its outer surface would extend beyond Jupiter's orbit. Massive stars like Betelgeuse have short lifespans and often meet their end in spectacular supernovae. These explosive events are not only visually stunning but also play a crucial role in the universe's evolution by dispersing elements like carbon, nitrogen, and oxygen, the fundamental building blocks of life as we know it. The death of stars like Betelgeuse contributes to the genesis of life elsewhere in the cosmos. Could it be possible for a massive star like Betelgeuse to simply fade away without a dramatic finale? The answer is both fascinating and complex. Several theories have been proposed to explain this phenomenon. One prevailing theory suggests that dust clouds surrounding the star are obscuring its light, leading to the observed dimming. As stars like Betelgeuse age, they often shed their outer layers, releasing substantial amounts of dust and gas into space. This material can create thick clouds that occasionally block the star's light, making it appear dimmer from our perspective. Subsequent observations reveal that Betelgeuse has been producing increased amounts of material, contributing to such dust clouds. This process is a typical aspect of a star's life cycle, especially for red supergiants like Betelgeuse. Another theory involves stellar pulsations. Massive stars such as Betelgeuse frequently undergo cycles of expansion and contraction. These pulsations can cause variations in brightness, with the star dimming during contraction phases. This behavior is expected for stars of Betelgeuse's type, as the star's immense gravity pulls its outer layers inward while heat from the core pushes them outward, causing expansion. However, the most alarming theory, which has garnered significant attention, is that this dimming could signal an impending supernova. Are we on the brink of witnessing one of the most monumental events in our galaxy? The life cycle of a star is determined by its mass, and Betelgeuse, with a mass 20 times that of our Sun, is destined to end in a supernova. The sudden dimming may indicate that the star is depleting its fuel and is about to collapse under its own gravity. Generally, stars that have experienced sudden dimming have sometimes exploded in spectacular supernovae. These blasts are not only visually magnificent but also play a crucial role in the evolution of the universe by scattering essential elements into space. The JWST has been monitoring Betelgeuse long before any potential supernova event, utilizing its suite of advanced instruments, including the near-infrared camera, mid-infrared instrument, and near-infrared spectrograph. The JWST has gathered a wealth of data on Betelgeuse, capturing high-resolution images, analyzing the star's light spectrum, and detecting subtle changes in its brightness and temperature. Given this advanced technology, how did the JWST identify changes in Betelgeuse leading up to a possible supernova? The data collected by the JWST is striking. For example, the mid-infrared instrument, MIRI, can detect heat emitted by the dust surrounding Betelgeuse. This dust, resulting from the star shedding its outer layers, provides valuable information about the star's evolutionary state. In exploring the remnants and light produced by Betelgeuse, astronomers can reconstruct the star's past, current state, and future possibilities. This massive red supergiant has long fascinated cosmologists with its sheer size and brilliance, but it is the mysteries surrounding it that truly ignite the imagination. Betelgeuse is classified as a variable star, meaning its brightness fluctuates over time. While many stars exhibit such behavior, the variations in Betelgeuse are particularly pronounced. These fluctuations have been observed for over a century and were initially thought to be normal. However, recent observations have indicated they are more erratic than previously believed. This unpredictability adds another layer of intrigue to this already enigmatic star. But what causes these changes? As a red supergiant, Betelgeuse has a tumultuous interior filled with nuclear reactions. Hydrogen atoms fuse to form helium, generating immense amounts of energy. This energy pushes outward, causing the star's outer layers to expand. As these layers expand, they cool down, resulting in a decrease in brightness. When the outer layers contract again, they heat up, increasing the star's luminosity. This cycle of expansion and contraction leads to the brightness variations we observe. Each pulse of Betelgeuse provides astronomers with a glimpse into its internal structure, composition, and future. You might wonder why stars have different colors. Why some are blue, others yellow, and others, like Betelgeuse, a brilliant red. A star's color is directly linked to its temperature. Blue stars are the hottest, with temperatures reaching up to 30,000 degrees Celsius, while red stars are cooler, around 3,500 degrees Celsius. Despite being considered cool, Betelgeuse would still burn you if you got too close. Another fascinating aspect of Betelgeuse is its age. It might seem counterintuitive, but massive stars like Betelgeuse have shorter lifespans than smaller stars. This is because they consume their nuclear fuel at a much faster rate. Betelgeuse is nearing the end of its life and will eventually explode as a supernova. This explosion will be so bright that it will be visible even during the day, overshadowing all other stars in the night sky. The pressing question is, when will this happen? Predicting the exact moment a star will go supernova is challenging, but the recent dimming events have led many to speculate that Betelgeuse's end may be closer than we think. Could we be witnessing the last days of this celestial giant? One crucial reason to believe that Betelgeuse could go supernova soon is its age and position in the cosmic life cycle. As mentioned, massive stars like Betelgeuse burn through their nuclear fuel much quicker than smaller stars. Betelgeuse has already exhausted the hydrogen in its core and is now fusing heavier elements. Each successive fusion stage produces less energy and lasts for a shorter time. As the star fuses progressively heavier elements, it develops an onion-like structure with layers burning different elements. Once a massive star starts fusing iron in its core, it becomes a ticking time bomb. Iron fusion does not generate energy but rather consumes it. This process leads to a rapid collapse of the core followed by a rebound shockwave, resulting in a supernova explosion. Another variable fueling this belief is the star's significant dimming. While dimming can be caused by various factors, such as dust clouds or cosmic pulses, the rapid and substantial decrease in brightness may also indicate that the star is nearing the end of its life. Before a star goes supernova, it can shed a substantial portion of its outer layers, contributing to these dimming events. If Betelgeuse were to detonate, the explosion would be one of the most significant cosmic events in recent history. While the spectacle would be breathtaking, the consequences of a Betelgeuse supernova would ripple across various domains, from immediate impacts in space to long-term implications for our understanding of the universe. Imagine the immediate aftermath of the explosion. Betelgeuse going supernova would generate a brilliant outburst of light, surpassing every star in the night sky for weeks, potentially even months. This once familiar star would transform into a beacon in the sky, visible even during the day. The night sky would be altered, with Betelgeuse's brightness rivaling that of the full moon, dazzling casual observers and offering a unique observational opportunity for astronomers worldwide. However, this luminous display is just the beginning. The energy released during the supernova would equal the total energy our Sun will emit over its entire lifetime. The explosion would send a shock wave through space, compressing and pushing the interstellar medium in its path. As this shock wave travels, it would heat the surrounding gas, creating a glowing bubble of ionized material. This remnant of the supernova would continue to shine for millennia, serving as a lasting testament to Betelgeuse's explosive end. Beyond the immediate vicinity of the blast, the supernova would emit a torrent of cosmic rays and high-energy particles traveling close to the speed of light. These particles, primarily protons and atomic nuclei, would spread in all directions, with some ultimately reaching our solar system. While Earth's magnetic field and atmosphere would shield us from direct effects, these particles could interact with the solar wind, potentially enhancing auroras and making them visible at lower latitudes than usual. The explosion would also release a significant amount of gamma radiation, the most energetic form of electromagnetic radiation. While much of this radiation would be absorbed by the interstellar medium, some could reach our solar system. Given Betelgeuse's distance from Earth, this radiation would not pose an immediate threat but would contribute to the background gamma radiation detected by satellites and space telescopes, providing valuable data for astrophysicists studying high-energy processes in the universe. On a deeper level, the materials ejected during the supernova would enrich the interstellar medium with heavy elements. Stars like Betelgeuse are colossal factories where elements heavier than hydrogen and helium are forged. When such a star detonates, it disperses these elements into space. Elements like carbon, oxygen, nitrogen, and even metals like gold and platinum would be scattered throughout the universe, fertilizing it with the raw materials necessary for future stars, planets, and potentially life. From a poetic perspective, We owe our very existence to the deaths of stars. The carbon in our cells, the oxygen we breathe, and the iron in our blood were all formed in the hearts of stars that exploded long before our solar system was born. Furthermore, the remnants of the explosion would provide a treasure trove of information about the life cycle of massive stars. By studying the layers of material expelled during the supernova, astronomers could piece together the star's history and gain insights into the processes that occurred in its core during its final days. This would yield invaluable knowledge about cosmic evolution, nuclear fusion, and the mechanics of supernova explosions.